Next up, we would like the Lewis structure for NO+, and will it be shorter, longer, or the same length as the nitrogen-oxygen bond in NO? And explain why. So let's begin by drawing out their two Lewis structures. For NO, we are going to count the valence electrons. We will have 5 plus 6 minus 1 because of the charge, and that's going to give us 10 electrons. Let's begin by making one bond in between them and adding in our valence electrons. And so this way we'd have 6 by 2 plus 2, and so that's going to give us 14 electrons, which are clearly more than the 10 that we have available. So let's begin by adding another bond between them, which would leave 4 on each of them. And now we can begin to count. We have 2, 4, 6, 8, 10, 12. So again, now instead of having the 14, we have 12 electrons, which is still more than the 10 that we have been given. And so how we can fix this is to add another bond in between them. And now we have 2, 4, 6, 8, 10. And so all of our electrons are now accounted for. And we can go about checking the formal charge. For our formal charge of nitrogen, we are going to have 5 minus the 3 in these bonding pairs minus 2, giving us 0. On the oxygen, we will have 6 minus the 2 in the lone pairs minus the 3 in the bonding pairs. That's 6 minus 5, which is going to leave us with a positive 1. So let's just put that on it. Does that make sense? We're told that this is NO+, so yes it does. So the formal charges are all taken care of, and our valence electrons are all taken care of. And so this is the Lewis structure for NO+. Let's go about doing the one for NO, and then we can compare them. NO, we have for our valence electrons, 5 plus 6, giving us 11 electrons. And so if we begin with one bond in between them, we start like that. If you count them out, we'll have 14 again. So what we can actually do is, again, instead of doing double bonds this time, we can actually cancel out octets. And we know that this will happen because it's 11 electrons, which is an odd number. So you're expecting radicals to appear somewhere. And so we're allowed to take out these electrons because a radical would apply an underfilled octet. And so now we have 2, 4, 6, 8, 10, 12. Which is still 1 extra. So let's go about canceling out that one. And so we'll have 3 electrons on the nitrogen, and oxygen will still have its filled octet. It would be tempting to do the opposite and have oxygen with the underfilled octet, but we'll see why when it comes to the formal charge in just a minute. Here we will have a formal charge on the nitrogen of 5 minus 3 minus 1. And so that would leave us with a positive 1. And on the oxygen, we will have 6 minus 6 minus 1, leaving us with negative 1. So we're going to have a negative charge here and a positive charge here. This makes more sense. We'd like to have the negative charge on the oxygen. In this case, we won't see that. Instead, we'll have nitrogen with 5 minus 6 minus 1, so negative 2. And oxygen with a charge of 6 minus 3 minus 1. So positive 2. So we have larger charges and we have the positive charge on oxygen, which is not preferred. So clearly this is not going to be correct. And so that's why we chose to take the electrons off nitrogen instead. And so this is our final structure. And so now we need to ask ourselves what things determine the bond length. And what determines the bond length is the bond order. If you have a molecular orbital diagram, that can be calculated by the number of bonding orbitals minus the number of anti-bonding orbitals, all over 2. If we have the structure as we do here, it can simply be counted as the number of bonds. And so here, we will have a bond order of 3, and here, we have a bond order of 1. We know that the higher the bond order, the higher the bond energy. And that means the shorter the bond length. The reasoning for this is because if the bond energy is higher, that means we have more repulsion, which means that the two must be closer to each other than if the bond energy was lower. And so what that means is that a bond order of 3 that's higher than 1 is going to have a higher bond energy than in this case, which means its bond length will be even shorter. And so the answer to the question of between NO plus and NO, which one has the shorter bond length, is going to be NO plus. And that's your final answer. And it's explained by the concept of bond order.